Look at this 1960s-era casino floor. Between the ringing slot machines and the noise of the craps tables, the environment is designed for sensory overload. The games here, slots, roulette, and craps, rely on independent chance. Every roll of the dice is a reset, ensuring the house maintains an unbeatable statistical edge. In the middle of this chaos sat Edward O. Thorpe. He was a lanky math professor who brought a different set of tools to the blackjack table: cold logic and a Vincent Bach Stradivarius trumpet player's discipline. Thorpe holds a jack and a 10, a hand totaling 20. Conventional wisdom says you never split tens, but Thorpe does exactly that, splitting the hand 4 times and placing massive bets on each. He finishes the round with 4 winning hands. The victory was short-lived. Casino management immediately intervened. Security guards dragged Thorpe from the table, and the manager warned him that next time he might find himself lying face down on a cactus. Thorpe had solved a game the industry considered unbreakable, but his experiment highlighted a practical reality. The best math in the world is useless if the house won't let you stay at the table. Thorpe's system didn't begin in the casinos. It started in the theoretical world of mid-century academia. At UCLA, Thorpe and his colleagues began looking at gambling not as a test of luck, but as a series of highly complex, mathematically solvable equations. To understand his breakthrough, consider a standard lottery. The odds are roughly 1 in 2.6 million. Because the machine resets with every draw, your chances never improve. This is independent probability. Blackjack relies on dependent probability. Every card dealt is permanently removed. If low cards are pulled, the remaining cards are more likely high value. The mathematical advantage shifts toward the player. Mapping these advantages required massive computational power. Thorpe worked with Julian Braun and the Four Horsemen, using early mainframes, like the one seen here, to run millions of calculations and map out massive, highly complex decision trees. This data produced the 10-count strategy, proving that a player could identify the exact moments when the edge vanished. These theoretical expectation values worked perfectly in a controlled laboratory. However, the researchers knew that a player standing at a table and performing like a calculator would be spotted in minutes. When the team moved their testing to Reno and Lake Tahoe, they realized the underlying math needed a disguise. To stay at the tables, they had to hide their intellectual advantage. Thorpe developed a second, practical system he called Stanislavski for card counters. Named after the famous acting teacher, it required the team to adopt complete personas to deceive casino surveillance. At Barney's Casino, these brilliant mathematicians wore pristine ski vests to look like wealthy, completely clueless tourists who had just come off the slopes. They used behavioral misdirection to maintain the rube persona, asking the dealer basic questions like, "How do I ask for a card?" to build the complete illusion that they had no idea how to play. This camouflage allowed them to vary their bets without raising suspicion. They bet low when the deck was cold and dropped massive bets when the math turned in their favor. Advantage play combined these linear operators with high-stakes theatrical misdirection to create a winning system. This photograph shows the dealer's deck, which became a primary battleground. Once Thorpe's system became public, casinos altered their rules, moved their shuffle points, and introduced multi-deck shoes to dilute the player's mathematical edge. The publication of Beat the Dealer started a permanent cat-and-mouse game between card counters and casino surveillance that still defines modern gambling security. Thorpe used the specific odds of the lottery to demonstrate that what most people call luck is often just a set of unfavorable numbers. He showed that when the math is understood, the mystery of the game vanishes. Thorpe's contributions to probability theory are recognized in academia as a form of intellectual immortality. He took the chaos of the gambling floor and showed that it operates on a foundation of predictable mathematical causes.